Good morning, Foundations of Algorithms. I am really very excited to see all of you again. It has been a couple of weeks. I hope you're feeling refreshed. And also now we have our first assignment out. While it may look a little bit scary and intimidating, hopefully once you get started, you'll see that it's actually quite enjoyable. You'll learn something new, and along the way, get to practice some of the skills that you've been developing so far. Now, up on screen, I have our historical figure for the week, and this is Michael Rabin. And if any of you have been paying very close attention to the computer science news, you'll actually know that he passed away in the last 2 weeks. And so Michael Rabin, coincidentally, turns out to be a really good figure for us to talk about this morning. He was born in Breslau and left Nazi Germany. He was a Jewish man and was fleeing persecution. He left in 1935 and studied mathematics at Hebrew University and later completed his PhD at Princeton University. So along with many of the other people we're going to see for the rest of semester, he was a winner of the Turing Award, the highest award in computer science. He won for his 1959 paper, Finite Automata and the Decision Problem, which is one of the foundational papers that we're actually going to talk about some of the concepts contained in it later today when we study one of our new algorithms. He was also a major pioneer of algorithms that use randomness to make them work. And one of the very big contributions was the introduction of the Miller-Rabin primality test, which is a really fast algorithm that allows you to tell with very high probability, whether a number is prime or not. And we use this all the time in practical cryptography. He also wrote one of the major string pattern matching algorithms, which is something that we're going to talk about today. Not quite his algorithm, but he wrote another one of the really big ones. And these are the kinds of achievements that are significant enough to win you the Turing Award, the highest award in the field of computer science. So now sit back for a moment, and we're going to take a dip into a different subject. Do we have any biology majors here? Or anyone doing Bio 1 or Bio 2? Got a couple people? Okay, so maybe you'll feel a little more comfortable for the next 3 to 5 minutes. Good morning, everyone, and welcome to Biol 1001. And so today we're going to talk about the process of DNA transcription. And in particular, I am interested in one particular problem that some people have in their DNA code, and this is called HFE hemochromatosis. Now, on the final exam, I'm going to ask you to replicate a diagnostic pattern that will identify whether a particular individual has HFE hemochromatosis, and this is essentially an excess of iron deposition that can occur in people's organs. This is in about 1 in 500 people. And the good news is, if we discover that someone has HFE hemochromatosis, we can intervene early if we detect it. And so you might ask, well, how do we biology students detect HFE hemochromatosis? Well, we're going to have to find the mutation in an individual's code, in an individual's DNA. And the way we're going to do this is through a process of biological pattern recognition. So we're going to use some enzymes to cut up the DNA and to read it out. We're going to use restriction endonuclease, RSA, to cut up our DNA. And then once we've cut up the DNA into fragments, we're going to amplify those fragments using polymerase chain reaction, or PCR, which many of you might have heard about a few years ago when people were talking about the tests that you could use to get COVID with. Those were PCR tests, which were essentially amplifying DNA that you would give a sample of to the testing center. And then once there was enough DNA, it would become much, much easier to read it out. So once we've done this PCR reaction, we're going to read in the whole sequence into the computer and then look for the particular change that causes this mutation, the change that is this mutation that causes HFE hemochromatosis. And what does this actually look like? Well, here's a strand of DNA that I've written out the code for you here. It's written out in base pairs, and these are the letters that you can see. And we can see in this where in the DNA segment the restriction endonuclease is going to cut. And then within those segments, we're going to look for this pattern that we see in our mutation. It's a little hard to see on this screen, but you can see that over there, that G, that guanine, has been turned into an adenine. That G has been turned into an A. Now, I know we're all biology students, so we're going to have to rely on the computer scientists to help us find this pattern within the larger DNA code. And somehow, I don't know how they're going to do it, who knows, but they'll use some algorithm, and then that algorithm is going to scan through the DNA and look to see if this mutation is indeed present. And so with that, we're going to have to cut this lecture short at 10 minutes, and I'm going to go and get my friend Dr. Connie from the computer science department to tell us about how this algorithm might work. So I'll see you all later. Good morning and welcome to Foundations of Algorithms. I'm Dr. Connie, and my friend from the biology department told me that you need to do string pattern search. Is that right? That's right? Okay, good. I'm in the right place. Well, I've got some bad news for you, and the bad news is that the algorithms that we learn at the start of first year aren't really going to be good enough to search through DNA. So we're going to need some fancier algorithms, some better algorithms that can do this more efficiently. But for now, let's stick with the brute force version of the problem. So I know you're biology students, so don't worry about the math too much. We will get through this together. But here is a more mathematical representation of that DNA problem that we were talking about. So let's say we have a sequence of characters, and let's call this sequence of characters T, and there are going to be n characters, so in an array they're going to range from 0 to n minus 1, and we'll have some pattern that we're looking for, a pattern of length L, and so the indices in the pattern are going to range from 0 to L minus 1. So our job is to find an index k, find a place somewhere in that large string. We're going to look for a pattern somewhere in that large string, and we're going to call that place that we've found k. And what we're going to say is for every j in the pattern starting at location k, up until we've hit the length of the pattern, make sure that each of those locations is identical to what we would expect in the pattern. So what we want to do is we want to look for a given pattern inside our string. So let's say our string is the letters A to H and our pattern is C, D, E. We want to look for a location inside the string where our whole pattern begins. And that's the same as saying, okay, if we're at location K in the pattern, and if we're at location K in the string, look at location 0 in the pattern and see if it matches. Okay, if it matches, let's look at location K plus 1 in the string. Does that match location 1 in the pattern? Now, what about K plus 2 in the string? Does that match location 2 in the pattern? It does in this case only when K equals 2. And so what we're trying to do is find that value of K such that this is correct. And now, while the mathematical notation here may have looked intimidating, it's actually straightforward once you break it down into its component parts. And in fact, we don't use this notation all the time because it is a little confusing. And confession, I found again last night when I was looking over the slides that this slide had been wrong for 5 years and no one had picked it up. So again, the mathematics is there to help formalize and help communicate the idea. It's not there for the sake of being complicated. It's more there for precision, but sometimes we're imprecise and still get it wrong. Okay, so let's build up what our solution is going to look like for this problem, our most naive, our most brute force version of this, in order that we can find the mutation, hopefully efficiently, but at least find it in the first place to start with. So we'll use a couple of intuitions to build up our algorithm. And what I want to do in this lecture is kind of show you how you can go from only a little bit of knowledge about the problem that you're trying to solve and go from there into thinking, okay, what would an algorithm look like that solves that problem? What are the steps that the people who invent algorithms go through to try and construct them? So here's our first intuition. Our first intuition is that if there is a matching pattern inside the string somewhere, it's got to start at some index k within the string. Now, seems like a totally stupid thing to say, of course. if there is a pattern, it's going to be inside the string. It has to be inside the string. But sometimes writing down these very obvious things, just like we did with our invariants in other lectures, can actually be a very useful way of starting to formulate what the algorithm itself looks like. So feel free to write down the stupid facts or the seemingly obvious facts when you're trying to solve a problem. And that's true from what we do in class, but also to your assessments as well. Can be a helpful way of getting the hang of things. The next kind of pertinent fact that we can think of, let's say we have a pattern of length L. A match essentially means having this property, such that from all indices k to k plus L, so where L is the length of the thing we're looking for, there must be a match between the thing and between the original string and between that corresponding position in the pattern. So we don't know where in the string this is going to start happening. We don't know where this location k is, but we know once we hit location k, until we've gone the length of the pattern, we're going to see that pattern just verbatim. And so we're going to be able to match what we see in the original string with the pattern if we've correctly found that position. And then intuition 3 is that a matching pattern of length L cannot be found if we're already too close to the end of the string such that there are not L letters left to look at. So if you're looking for a pattern of length 5 and you only have got 2 letters left to look at in the string, that can't work. So that's going to give us some bounds on our loop that we'll eventually be using to try and find our pattern. So put these facts together with one more. You can tell that the pattern doesn't start at a given location as soon as you find the first non-matching character. So if our pattern is 9 characters long, but we've gotten 3 characters in and we've already found that it doesn't match, there's no need for us to check the other 6 characters to know that we're not at the right place. Imagine that you're looking for the word cat inside the word battery. There is no C inside the word battery, and so you don't need to check the A and the T for every position. You just need to check the C. And as soon as you know that there are no C's in there, you know that there's no matching character for that first position. And so you know that you're not going to find a whole match for the whole word anywhere. And these are all the intuitions we need. Oh, for A, I should say. There's one extra little intuition. If the pattern is of length L, and you've checked L characters, and you haven't errored out already, that actually means you've correctly found the pattern, because there's no way you could have gotten to the end of the word cat and ticked off the T as well if that whole pattern isn't actually correct. So a bunch of seemingly like kind of straightforward intuitions. There's no magic here. There's nothing complicated. It probably feels a little funny to you that I'm going over these seemingly obvious facts, but if you put these together, that's actually pretty much our whole algorithm. So let's combine them, and this is what combining the facts would look like in an algorithmic sense. So test each possible index in the string T for a match. That was from our first intuition, that if there's a match, it's going to be at some index inside the string. And then in order to test for a match, check if the current index of the string and the pattern match. If they do match, if they don't match, then move on to the next character, because we know that that can't be the correct starting place. And if they do match, move along one position in the pattern and in the string and check if they match at that subsequent position. Now we have to be careful here, as if we've gone like 2 characters, let's say we've gone 2 or 3 characters along and we finish and we know we haven't found a match, we still have to check the next possible starting position for the pattern. So let's say we're checking position 3 in the overall string, and we get 4 out of 9 characters through the pattern. When we've done that, we have to go back to position 4 in the string to now see if position 4 is the place where that pattern exists. We can't just say, oh, I checked another 4 characters through my pattern, so now I don't have to look at those starting positions in the overall string. And we'll see a demo of that in a minute, so it's a little more concrete. So what's the running time here? So how many possible starting positions are there?
It's not the length of the pattern?
Not the length of the pattern, but close. So it could start at position 0 in the string, it could start at position 1 in the string, it could start at position 2 in the string. How many possible positions are there? The string is of length n.
N minus 1.
Yeah. But if we want to be super precise, and this wasn't the question I was asking, but if we do want to be super precise, then we can say, well, not all of those positions are actual possible starting positions, because we had that extra fact that, like, if we've gotten close to the end and there aren't enough spaces left, then the pattern couldn't possibly begin there. So if we want to be super precise, we can say n minus l plus 1. But we're computer scientists, so we throw away the small things. So there are really n possible indices, and we're going to throw away that small constant, because in our DNA example that we're talking about here, and in most examples of this problem type that we care about, the pattern that we're searching for something in is going to be, the string that we're searching for something in is going to be much, much larger than the pattern. So n, the length of the string, is going to be much, much larger than l, which is the length of the pattern. And so we just say, it's going to be like n possible positions. And then for each position, how many letters do we have to check in the worst case?
So it could be checked from index 3.
Yep.
Yeah, and until the end, but...
So let's say I'm looking for the word cat, and I'm checking at position 3. How many letters do I need to check until I know if I've found cat or not? 3. So that's the length of the pattern, rather than the length of the string. And so the worst case here is going to be L letters. So I have n possible places to check, and at each place I have to check maximum of L letters. So what's going to be the big O overall then?
Times together.
N times L. Yep. So we have an n times L algorithm. So I can write it out like the pseudocode I have, or put it in a slightly more concrete version of pseudocode, which this is a version that I've constructed to look a little bit more like C, but not quite there. And if we look, we can see we have 2 while loops in here. And the first while loop goes through while s is less than n minus l, which L is small, n is big, so let's just say that's n. And then the second one is while I is less than L, so that's checking, okay, is it the C from cat? Is it the A from cat? Does the T from cat match? So we can see outer loop n times, inner loop L times, that gives us big O of NL worst case. So not so bad, linear time. Wiki, do you want to pass the microphone to Devansh?
Oh, sorry, I just realized my question was bad because L is like a constant of sorts.
Yeah.
So it's basically like, in effect, it's not really ONL, like you'd actually just write it as ON perhaps.
Yeah.
I thought it was like L is also a variable like N.
It could be. It's up to you to define how you want to talk about the problem. So you could say, well, the problem is we're going to run this a bunch of times with, we're going to run this 10 times with 10 different patterns. And you could say, well, let L be the longest pattern that we're searching for. So it depends, like, if you're a bit more precise about the phrasing of the problem, you could say, okay, this one's a constant, that's not, but it really depends on the details of how you're phrasing it, which we're not worrying about for now. Okay, any questions so far? That should be pretty straightforward. We're happy? Okay. So let's look at this string. We're looking for the pattern, how many A's are there? 6, 7, 8 A's and a B. And that is our pattern of length L, so it's 9 letters long, and then our string is of length N, and it's all A's. So how is this going to work? Well, let me sketch it out on the iPad, and we're all going to get bored pretty quickly, which is the point. Let's check position 0 to see if our pattern AAAB matches the string at position 0. Okay. So position 0, does A match with A? Does A match with A? Does A match with A? Does A match with B? No. Oh, okay. That's a bit sad. So I guess we should check the next position along. Does A match with A? Does A match with A? Does A match with A? Does A match with B? Okay, let's check the next position along. Does A match with A? Does A match with A? Does A match with A? Does A match with B? Okay. So this has revealed something not so fun about our algorithm, is that we get this worst case when there's a lot of overlap between the pattern and the string, that we're going to search we could search up to all the letters except the last one through the pattern, and then get a mismatch, and then have to move on again. That's exactly what's happening here, all the way up until the end. So this is what our worst case looks like. N minus L times total, and then each time that we're checking a new index, we're doing all those L comparisons again. And you might already be getting a sense that we're wasting some energy here. So one thing we could say is, well, on average, you won't even match the first character, because how many characters are there in the English language? 26. And so if I pick a random pattern and a random word, well, not a random, let's say I have a random pattern and a random string in English, what's the probability that the first letter between the two of those is a match? And what was your name? Thomas. Okay, Thomas, what is the probability that if I have a random pattern and a random string, that the first letter of them match, assuming I'm doing English just lowercase? 1 in 26. Now let's assume that I'm using an actual word from English and a random pattern. Why?
Like, not as many words start with the same character, like letters, like Z, X.
So the challenge there is, even though the distribution of starting letters in our string might be biased, our pattern is unbiased. And so we've still got that 1 in 26 interaction. But if we take that one step further and say, well, what about if we're searching for an English substring inside an English word, then we're actually going to get that relationship between the two starting to take effect. So knowing that on average we won't even match the first character, this is where we get what Devansh was saying about. Really, we're talking about over n time average case for pattern search, assuming no extra things over the distribution of the pattern and the strings, other than that they are written in English letters. Now, one of the themes that we're going to see towards the very end of today and maybe the start of next week is, at times you will be able to get distributional assumptions in your algorithms, and these will actually allow you to improve them, because we've got already our 1 in 26 thing here, but maybe if we know something about the distribution, we can improve our pattern search. But there was something that seemed really bothersome about the algorithm that we were using before, our brute force version. Thomas, do you have a sense of what it was that was really annoying about it, that seemed unnecessary?
B wasn't even in the string.
So aside from the fact that B wasn't in there, so that's true, B wasn't in there, and so no matter what we did, we wouldn't have found it, but it still took us a lot of steps, didn't it?
It was like, there's lots of overlap.
Say again?
Lots of overlap.
Lots of overlap. So let's go back to that. That's exactly the intuition, and I'm so glad you found that. So let's go back to our picture, and let's see if you can tell me where the overlap or where this wasted work is happening. Okay, so obviously when I start, there's nothing I can do. I haven't seen anything yet, so I can't gain any advantage. I have to look at the first letter of the string, and I have to look at the first letter of the pattern, nothing else. Okay, so let's do that. Does A match with A? Does A match with A? Yeah. Does A match with A? Does A match with A? Does A match with B? No. Okay.
But then when you go again, you're rechecking if A matches with A. So could you use that?
Well, yes, but expand on that a little more for me. Make it really, really explicit.
Could we just store somewhere that we know that position 0 is A?
Position 0 in the pattern or position 0 in the string?
String is A. So could we use that? Or not 0. 0 is once we move on.
Yeah, we've already moved on from 0, so that's a good point.
We could be keeping track of 1, 2, and 3.
Yeah, so let's say that, let's be even a little bit clearer about that. So we know a relationship between the pattern and the string at this point already, don't we? What relationship do we know?
The first 3 or a match.
So we know that the first 3 were a match, But more than that, you talked about overlap going on here. So we know that in the pattern, there are multiple A's, and also in the string, there are multiple A's. And so by the time we get to checking that second position, we can say, the pattern itself has an A both in position 1 and in position 2. So we know that if we matched in both position 1 and position 2, that means that position 2, we shouldn't have to bother rechecking it. Why? Well, these are the same. Those two A's are the same in the pattern. These are the same. Right? And let's say we record that fact. And we know, therefore, that this must have also been equivalent to a match the first time we checked through. Now, let's do that a little more slowly and see why. And I'm going to reverse a few of our steps here. Move that back. Okay. So we matched position 1 in the string with position 1 in the pattern the first time around. We also have this additional piece of information that we know that these two are the same, and that gives us a transitive relationship here. That means that these two must be the same, and that means that on the next time, when we move things over, we don't need to bother checking this one here. We don't need to bother checking that because we already know it by the virtue of having done that work previously. Now let's take that a step further. Let's take that a step further. If we look at our pattern, it's not only the first 2 letters are the same, but tell me something else, Thomas?
The first 3.
The first 3 letters are the same. Okay.
So does this mean once we've done our initial check of 3, we only need to be checking 1 every time afterwards?
You've just about got it.
Yeah.
So we know that these two are the same, and we know that all 3 of these are the same. So we can say, well, if we've just matched those 3, so when we move it along, we already know by our transitivity property that we had before that this must match with that, and that must match with that. And so we can just continue checking from here. Now, of course, if we'd matched the whole pattern, we wouldn't need to do that. But what this is essentially going to allow us to do is to develop some kind of memory about the things that we've already checked. Now, you'll notice that we were talking about relationships here. Which of the relationships are going to stay the same no matter which position in the string we're checking? Let's imagine I am covering up. I'm going to draw a thing to cover all of that up. Maybe I'll move it along a little bit. Which of the relationship do we know no matter what comes next? Which relationship that we've already recognized?
3 A's in a row.
In
a row, like together.
In the pattern or the string? Which thing doesn't change no matter what comes next?
Pattern.
In the pattern, yeah. So it's actually information about the pattern that we can compute once ahead of time, and once we know about overlap in the pattern, then we can reuse that. So we can say, I know that we've matched 3 characters into the pattern, which means that I must have overlap between things in the string as well. And so you can say, okay, we matched 2 characters in the pattern and then failed. That means next time I can save myself the effort of 1 extra check. Or if we've matched 3 along and failed on the 4th one, then I can save myself 2 checks, etc. And this is going to be a really big idea and the core underlying intuition behind our next algorithm. So we're up to Act 2 of today, which is having memory inside a single search that we're doing. So we're still doing one search, we're searching for one pattern inside one string, but by giving ourselves a little extra memory, by doing some work ahead of time, and then storing some information as we go, we can actually reduce the number of checks that we do so that Thomas doesn't get stuck telling me that A matches with A matches with A matches with A over and over again. Now it is going to get a little more complicated as our pattern gets more complicated. This was the easiest way of demonstrating it, but the core underlying idea is going to be the same. And ideally, what we're going to look for here is worst case linear time. And we're going to need a new tool for this. There are lots of ways of talking about the next algorithm that we are going to explore. And I'm going to show you something called finite-state automata, and that sounds really, really complicated, but the core idea is really simple. And it's another way of describing an algorithm that sometimes might be an easier way of thinking about certain problems. Now, in computer science, there are always deep equivalencies between like one very mathematical representation and the code representation. This is another representation, and it's somewhat pictorial as well, that we can use to understand algorithms. And we're going to use this to build on Thomas's idea of figuring out how we can store this information and how we can kind of use that to change what our algorithm is doing at any given point in time. And also just thinking back to our very first slide of class, because this was quite a significant moment for many of us in computer science, finite-state automata were one of the important contributions of Michael Rabin. So he didn't invent finite-state automata overall, but made really, really key contributions that led us to where we are today. So the simplest finite-state automata you encounter every single day, and there's a hint to how that works on the board. And thank you very much, Thomas. Can we have a round of applause for Thomas? And good morning. Remind me your name again?
Bethany.
Bethany. Okay, Bethany, do you know what that is?
Traffic light.
Traffic light. Okay, how does it work?
Red means you don't stop the car, don't drive. Yellow means slow down if you can. If not, keep going. And green means go.
So I'm a pretty bad driver. And so what I like to do is I see the traffic light go red, and then when it goes amber, I put my foot on the accelerator, and then when it goes green, after going amber, then I kind of let off because I've already sped up during the amber, and then from green, it goes to red, and so I just suddenly slam the brake down. What's wrong with my story?
You said it from green, it goes to red. It needs to go, and it goes amber first. It has like an order. It goes green.
Okay, it has an order. So explain this order to me.
So the light will start at green, then it will go to amber, and then it will go to red. So you're slowing down in preparation for it to go to red.
And then after red?
It then goes back to green.
Okay, so if you were describing this as an algorithm, what would you use to like kind of make this work? Give me the very high level picture. You're writing a bit of C code.
I would start it at a point and then like increment through like to like use like a for loop or something to increment through the different colors, either like through an array or something.
Close, but probably not how I would do it. I'd probably have it store the memory of what current color it's on, and then just use a simple if-else. So we'd have a while loop that says like, while however many times we need to change, if currently red, if previous state is red, current state equals green. If previous state is green, next state equals
Orange.
amber, yeah, or orange. And after that, what would the last one be?
Red.
Red. And so you've essentially created a finite state automata. That's exactly what this idea here is we're going to have some notion of what the current state is, and then we're going to have a rule about, based on what the current state is, what our next state should be. Now I'm going to give you another example in a minute, but this is a pictorial representation of everything we need to make a traffic light work. So we're going to have some start position when we turn the light on. So let's say it starts at green. It doesn't really matter in this case. And then we'll have a state, which is what color the light is currently. We'll have a transition. And in this case, for a traffic light, it's very simple. Every transition is the same. It's just go to the next color in the order. And then finally, for a finite state automata, we normally have a version when we've reached a solution. Traffic lights aren't quite like that, but close enough, and we'll see another example that does have this kind of accepting or final state. So here's a diagram of something else very similar. How many of you had a school locker that had one of these combination locks? Put your hand up if you had one of those. Okay, Bethany, you've had one, so you can help us understand it. So in this case, your code is 421731. So it starts at locked, right? You've come to school at the end of the day. And let's say you enter in 17. What happens? What state does the lock go to?
Locked.
Locked. It doesn't do anything. So let's look at our picture, and we can say if we're on locked and we have something that is not 42, anything else but 42, it just stays at locked. It goes back to locked. Okay, what if we are at locked and we enter 42? What happens?
Then it will go to A on the diagram.
Yeah, then we can move to our next state. This is not fully unlocked. This is not our accepting or final state yet. It's an intermediate state. And then if I'm at state A and I enter 42, what happens?
It will then become locked.
It goes back to locked. It resets. So even if you enter the first number of the combination lock correctly, if you enter the second number incorrectly, then you go back to the beginning again. And so what we need to do to get to our final state is we need to enter 42, then 17. Where does that take us, Bethany?
To B.
And then to unlock it?
31.
31. And that takes us to our final unlocked state, which we can represent here with this kind of double circle in our picture. Now, as Bethany was just describing to me before, we can also represent this in code in a bunch of different ways. One way we can do it is by writing out this nice table that says, if you are in this state currently, go to this state next if you receive this input. So just like in our picture, if you're in the locked state and you receive not 42, update your variable to say your state variable to say that you're still in locked. If you're in locked and you receive 42, then move to state A. And so we can write this out as a table. And in C, how do we often represent tables? Yeah, an array. This is essentially just like a 2D array where one column is the current state and the next column, one of our axes is the current state and the other one is the next state. And then our input is going to be the way that we figure out which of the ones we should go to. But now let's go to what Bethany and I discussed, and we can of course write this out in some simple C code. So here is a short version of combination lock code. And we're going to use this to follow up on what Thomas was talking about figuring out, okay, based on what we've already seen, what state am I in, and what does that mean about what I should do next? And this turns out, in my view, to be the easiest way of understanding the hardest algorithm to understand that we'll teach in this class. So let's go back to pattern search and draw out the finite state automaton, draw out this diagram for that search that we were doing with our pattern before. Here is our B search, and this is our pattern over here and not our string. And what I'm drawing here is the red lines will be if you mismatch at this point in the pattern, go back to looking at your pattern from this position. So our boring bad version of linear pattern search was if you mismatch at the third A, start again from the start of the pattern when you move to the next position in the string. So you searched at position 2, you did A, and then you hit your A and your B didn't match. Okay, follow the red arrow in our algorithm. The algorithm says, go back to the start again. Move over one position and go back to the very start. And this was our bad algorithm, but this is a representation of it that makes it very clear and obvious where the repeated work is coming from. Because no matter what you see, you always go back to the start. The only time that you succeed is if you go, we're at the start, I haven't seen anything and I've found an A, okay, I'll go to A1. I'm at the start and I see another A, okay, I'm at position 1 and I see another A, I'll go to A2. I'm at position 2, and I see another A, I'll go to 3, etc., etc. And the only time you finish is after 9 checks. When you're at A9, if you finally see a B, then you'd go to state B1, which is our accepting state. And so to make it just a little bit clearer, we're going to have 2 pointers that point to where we're up to in the pattern and where we're up to in our string. And what we're going to do is I can actually write out explicitly what my rule is. So if you follow one of the blue arrows, then what you should do is increment the pointer in both the string and the pattern. So check if the next position in both of them matches. And then if you follow a red arrow because you've mismatched, you're going to have to backtrack both of them. And you backtrack in the string all the way, and then you're going to move to the next position in the string to check if that next position is the starting one. And you're going to move back all the way in the pattern. So we've now seen this a bunch of times. And I'm not even going to play it through it because I think all of you have got the idea at this point. So now we're going to move to a slightly more complicated pattern and see if we can build on Thomas's idea of reusing the work. So here is what would happen if we used our naive solution. I'll show that one more time. And Bethany, do you have the microphone still? Do you want to pass it one to your left? Oh, to your right, sorry. My confusion. And what's your name?
Sean.
Sean?
Sean.
Sure.
Sean.
Awesome. So what are you noticing with this demo, with gel, pel, mel, ele, meleles? Is there repeated work we could be avoiding?
We have E and L. We know that for the pattern, it starts with E and L. So once we found that at that position it doesn't work, we can just not bother with the first letter of the pattern because we know that E and L goes together. And
Yeah, so you've just spotted kind of the opposite of what Thomas spotted before. So Thomas was saying, you know, in the pattern we had before with A, B, we've got lots of letters that are the same at the beginning. And now you just said, well, what happens if the letters are all different at the beginning? If they're different and we previously matched the first two and we've moved along one, then we know that can't possibly be the case. It can't possibly be the case that the pattern starts at the next position because we already know that letters 1 and 2 are different, and we searched both of those and there was a match on the first two, which means that the pattern can't possibly start at the next position in the string. Let's do that on the iPad and draw out that relationship and make it a little bit clearer. So here we have our new pattern and our new string. We're working our way up to finding HFE hemochromatosis, remember, and we'll get there. And we know a relationship between the E and the L. Are they the same? No, so let's put a slash through that. We know they're not the same. Now let's start our pattern search. Does E match with E? Does E match with L? Does E match with E? Does G match with M? Okay. So let's look at our pattern again. And we've got another thing that we know. We know that this E does match with this E over here. So let's go back here. We've got a few pieces of information about our pattern, and these are going to be relevant. We know that E and L at the start of the pattern don't match, but that the E in the third position matches the E at the start. So let's see what this would allow us to do. So I'm going to keep my 2 pointers at this point, S and C, and they're going to point to where we're up to in the pattern and in the main string respectively. So does E match with E? Does E match with L? Does E match with E? Yes. Now, does G match with M? No. So one thing that we could do is we could move the pattern over by 1 and then check if E and L match. But do we need to bother with doing this? Sure? Should I bother checking that position? Why not?
Because we know that the pattern starts with E and
Well, we know more than that. We know that E and L don't match. And we know that when we checked that position, the L matched with the L. So it's impossible for the pattern to start at that position because we already know something about that position. We know that it previously matched, but that the first location of the pattern and the 0th location of the pattern don't match. So we should really skip along. And now, is this another plausible position for the pattern to match? Yes, and should we even bother checking position 2 in the string with position 0 in the pattern? Or do we know something else? Have we already checked these positions?
yeah.
So if we go back before, we can see we knew that that matched, we knew that that matched, we knew that that matched. And so the first mismatch happened there. So when we move it along, we actually already know that these two should be a match because we know in our pattern that the first character in the pattern and the third character in the pattern are the same. And so this is leading us, we're almost there, to our very fancy string pattern search algorithm, our O of N worst case pattern search algorithm known as KMP or Knuth-Morris-Pratt. And the core idea of this is to look at the pattern ahead of time and check for overlaps between the start of the pattern and later parts of it. Because we know that when we've gone through the start of the pattern and matched up to a certain position, that if that sub-pattern appears later on, that we can reuse that information. So for a pattern with no duplicate characters whatsoever, let's imagine it is A, B, C, D, E. And this is different to our AAB example, and it's different to our LMLS example that has repeated characters. So for a pattern with no duplicate characters, what it's going to do is allow us to jump forward very quickly. Because we know if we've matched A, B, C, D, and then get a mismatch, the new pattern can't possibly start at any of those locations in the string because there's not another A. And so we're pretty happy with that. So let's develop out our KMP algorithm using the same process that we used to do our very, very basic string algorithm at the start. So come up with a couple of really kind of obvious intuitions and then see if we can put those intuitions together into an actual algorithm that uses some of what we've been discovering as we've tried running it. And this is how you might actually develop a real algorithm from scratch. Let's say you have a new interesting scientific problem, someone hasn't really developed a good algorithm. Doing this kind of exercise of, okay, what's the stupid version? What can I learn about it? Where am I seeing repeated work? These are the things you can use to actually build up your new version. So, fact 1. For any location S in the target string T, if a match starts at S, if that's where the match is actually correctly going to be found, then we know that location S in the string and location 0 in the pattern are going to be the same. So another way of saying that, if the word you're looking for is cat, you have to find a place in the string where the letter C appears. And at that location, they're going to match. Silly fact. Okay. Now, for all cases where I is bigger than C, the character at pattern C does not appear at pattern I. So this is our case where we had our string with no repeats. And this is what we're going to work on for the minute before going to one that does have repeated letters. So let's start again. We're going to start doing this with our pattern that has no duplicate characters to make it an easy version of the algorithm, which isn't quite there. And then we're going to tweak it so that it works for no matter what is in the pattern. So let's look again. This is the rule that says there are no duplicate characters. So if we've already seen a character earlier in the pattern, it's not going to repeat later in the character. What's the implication of this? Essentially, if we find a mismatch at some location C+1, that's just some index, we can move our guess for where it's next possible for us to find a match. We can move that along C letters. So that's the same thing we said before. If I've looked through A, B, C, D, and the pattern was A, B, C, D, E, if I've looked through A, B, C, D and they match, then I can move along at least 4 spaces because I know that I'm not going to find another letter A for at least 4 spaces in the string. And that's this rule here. So no duplicates in the pattern means skip as many characters as you've just matched. So we could write this out. At location S in the target and C in the pattern, if mismatch, skip C letters in the target, so in our string. But we have seen our AAAB and we've seen our LMLS example, and DNA is going to have an awful lot of repeats. Why, Show?
Because they only have 4 letters.
How many letters are there in DNA? How many base pairs?
2.
And they are, do you know?
ACTG, was it?
Yep, ACTG. So in DNA, we're going to have far fewer letters available, which means that our patterns are going to repeat much more often. So if the pattern begins to repeat itself, so if there are duplicate letters in our pattern, then we're not going to be able to skip all the way along. We're only going to be able to do a limited skip. So let's say our pattern had ABAC. It's possible that if we matched ABA already, then we already know there's another possible starting place because there's another possible A. And so that means we're not going to skip as many letters along on a mismatch. And so here's the rule that KMP uses. If the pattern begins to repeat itself in those I letters, skip only until you align the repeating part of the pattern. So if the pattern was ABA, BA, you've got duplicates going on there. And so what you want to do is you want to slide the pattern along and figure out, okay, where could the next pattern possibly exist in the target string based on where we saw those repeated letters. And this is what it looks like. So this is what we talked about with Thomas before. So in this case, each next location is a possible match still because we know that there are lots of A's, but we don't need to check the start of the pattern every time because we know that, well, we've got duplicate letters in the pattern, and so we've got this transitive relationship that because we know that we've already matched that much in the string, that we can't possibly find the letter B there. Now, what about for our LMLS one? Let's give this one a run. Now here, there are only some duplicates. So here we're doing a mixture of the two things. We're doing because there are a few non-duplicate letters. Sometimes we can just move along, but then we have to start at the start of the pattern again. And sometimes we do have this longer prefix, and so we can slide it along a larger amount. But that's helpful for an intuition, not yet helpful for us implementing the algorithm. We have to figure out, okay, how do we do this align the prefix thing? How do we figure out exactly how far along we can move? And this is where you're going to see a few different representations of what we call the failure function, or of the algorithm that helps us to determine how far along we should move and how many letters we should skip. And with that, we're going to take a 10-minute break. And welcome back to Foundations of Algorithms. We're now ready to look at our finite state automata, our picture that can tell us how much work we can skip depending on what we've already seen in our pattern and in our DNA so far, in our string that we're trying to match. So this is a pre-done version that I baked for you 30 minutes ago in the oven earlier that shows you, unlike our earlier picture where all the arrows all went back to the very start, this shows us how many letters we can skip based on how many matches we've already seen so far. And what the arrows here are showing is the furthest possible place in the pattern that we could be based on how much we've matched so far. So remember in our AAAAB example where we're looking for the string AAAB in something that has a whole lot of A's in it. If we've just matched 4 A's so far and we go along and we see another A, we should assume, just a guess, and it's okay to be wrong if we guess, we should assume that we're also looking at then position 3 in the pattern. That could be another matching place. So let's take a look at our example here, our LMLS one. So remember that we know that the E here matches with the E here. So if we mismatched when we got up to the M, what should we do? Let's say if we mismatch when we get up to the E here, where else in the pattern could we possibly be? Well, we know we've seen an E over there. And so what we do is we go back to this L state and we say, okay, we're in the L state. If the next letter is an E, that could be because it's the E at the very beginning, or it could be because it is the E over there. And so by jumping back, that allows us to check which of these places in the pattern are we actually at. If we see another E, is this an E that corresponds to the first E in the pattern, or is it an E that corresponds to the second E in the pattern? And based on what we've seen so far, it will allow us to determine that. And so it can be a little clearer if we color it up to try and make these arrows a little more visible. So in this case, I'm trying to show you all the places that go back to a certain position. So all the reds go back to the start, all the oranges go back to that E1, and all the greens are going back to L1 and E2. So now our next job is to take this pictorial representation and actually write it out as a table. So remember what we did with the combination lock when I said that we could write the combination lock out as a table or the traffic light example. If you are in green and you go to the next thing, then you're going from green to amber. Green can't go directly to red. And so we can write those out in our transition table. And we have some code to do that as well. And we'll go through the code in some more detail soon. But the structural features that you can see just by glancing at it is that we have this table over here that we're going to end up using, this failure table. And what this is going to be is this failure table will be just like the table that we used to write about the combination lock. So how do we fill up the table? Well, let's go to our picture and start actually writing down the equivalent numbers that correspond to where the arrows are taking us. So index here is just counting up where in the pattern we are. So position 0 is at the start, position 1, position 2, position 3, position 4, position 5, etc., etc., etc. And our cpos is going to tell us the index at which we'd have to go back to find that repeating portion again. So when we hit our E over there, if we want to find the other E that we've already seen before, that's at position 1 or index 1 in the pattern. So if we fail at this E, it could have been because we should have been looking from that E instead. And so we say, go back to position 1. Now let's look at another one. If we see this L over there, that L could have actually been this L. Remember, if we see an L in what we're looking for, we don't know which L in the pattern it is. It could be the later L or it could be the earlier L. And so the earlier L is located at position 2, which is over here. So that 2 matches with this 2. What about this E over here? Well, this E could be E at position 3. Why do we not explicitly say that it could have been that very first E? Because it could have been that very first E. Well, what we're going to rely on is this jumping behavior. So if we're at E4 and it wasn't E4 in the end, we check forward and it's a mismatch, so it wasn't actually a match. It could have been because we were meant to be at this E2 over here. And then we'll try and see, is it actually the E2 where we should have been? And if it isn't the E2, then we'll jump back to the E1. So at E4, we don't actually need to explicitly say, oh, it could have been all of the E's previously. We just look at the prior one, and then if the prior one mismatches, the prior one will tell us to go back to its prior one. And so by drawing these arrows, it helps us to see this kind of flow that, okay, if you're at E4 and you don't get and the next thing you get is not an L, go back to 3 over here, E2. And if the letter is not an M, that means see if you're at E1. And if you're at E1 and you don't get an L, well, then there are no E's to go back to, so go back to the start. Let's look at E5, similar kind of story. If we're at E5, it could have been, and we don't get an S, could it have been E4?
My question was regarding why E3. From E3, we jump right back to E1 and not to E2. So I understand why from E4 we would jump back to E1 because our sequence starts with ELE, but why are we jumping back to E1 from E3 and not E2?
From E3 to E1.
And not E2.
Yeah. So this is where that's what we were about to do. So good question. Let's go off what KJ said. So KJ said, well, if I look carefully at the diagram, it's not from every E you could go back to all the possible E's. You seem to have a different rule going on here, and that's actually totally correct. And this is the intuition that we were building towards. So the only places that we could be are where our prefix here, what's at the very start of the pattern, is also matching the suffix of the pattern so far. So that end bit. And so what we're looking for is a very specific type of overlap, not just duplicate letters. And so KMP is also known as the longest prefix that is also a suffix algorithm. And the reason I didn't say that up front is because that phrasing is really pretty confusing. And indeed, when I hear it phrased that way, I have to remember, okay, like, what's it a prefix of? What's it a suffix of? Which makes it confusing. So I think this is probably the easier way to start to look at it, is to take this approach and then kind of reverse engineer that part of it. So let's look at what's going on here. We have ELEM over here, and then the very next letters are ELE, and this ELE is a suffix. It's at the end of the part of the pattern that we've looked so far. And ELE matches the prefix at the very, very start. So what we're looking for is not actually individual letters that have been duplicated. We are looking for a suffix of what we've seen so far that also matches the prefix so far, because that's really our slide along rule. We're not trying to slide along random letters, because then we might get a bit where, like, okay, that E matches the same, but the next thing after the E doesn't match, and now I've forgotten exactly where we're up to in the pattern and in the string. So what we're looking for is a very clean slide over rule. So you know that if you've just seen ELE, it could be because it's this ELE. And so when we're jumping back, we're not jumping back just to the prior letter, we're jumping back to the prior pattern. And this is why our encoding is such that, let's go back to KJ's example, you were saying from E3 to E1? Is that the jump you were looking at? So let's look at when we have just done E3, what is our suffix? We've got a suffix that is E, we've got a suffix that is ME, we've got a suffix that is EME, we've got a suffix that is LEME, and we've got a suffix, and then we've got the whole thing, which is ELEMEL. So what is the longest suffix that is also a prefix? So there's no M anywhere there. So as soon as we go get our suffix ME, we know that that prefix can't be anywhere at the beginning anymore. So the longest prefix that we've got is just the letter E, and that's why we jump all the way back from E3 to E1. Now let's look at E4. When we go from E4, what we've just seen is ELE. That's a suffix too. And if we look, there's ELE over here. And so from E4, it really is plausible that we should have been imagining we were at this E2 instead. Why? Well, we know if we've just seen ELE, it could have been this ELE from this part of the pattern, or it could have been this ELE from that part of the pattern. And so we don't have to jump all the way back to that very first E, because it is plausible that our E4 actually should have been E2, were we getting a correct match. That answer your question? It was a very well-timed question. Do you want to pass to Oscar?
For the transition from E4 to E2.
E4 to E2, yes.
So that happens because you know that the next character is not an L. Wouldn't that mean that also it can't be E1? Because that would fail due to it not being an L, which you already know.
If we've just seen ELE, and then we try and go forwards, but the next letter we see isn't an L, our table tells us to go back to E2 over here. And if that fails as well because we don't see an M, then E2 tells us to go back to E1. And then we're doing this check for an L again, but we already checked before for an L, and we know that it wasn't an L. So why are we doing this repeated work? And the answer is that there's actually a trade-off here between how much we try to remember, how much work it takes us to look into our memory of what we've done, and how much work we can save by trying to do this memory thing. So in this instance, it turns out that the design of this algorithm, where we're kind of like bouncing back further along to different states, ends up being more efficient than trying to remember the precise details. So you are right, there is repeated work here, and this is something the algorithm didn't pick up on. And the reason is because the overall running time of the algorithm is not optimized to eliminate all repeated work, because that would involve other trade-offs. There are algorithms, other algorithms that do attempt to reuse some of this information, and they get a bit more sophisticated, and that's going to be beyond our class. How are we doing over there? Good. Okay. So let's now go one step further. So we understand this line, which is about which is about the position in the table that we need to go back to. We understand our index line, which is just telling us what number it is in the order, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. But now we want to do is actually calculate how much skipping we get to do. And the way to calculate skipping is very easy. Just compute the difference between where that position is and where it was from where it was that you were told to go. So if we're at this position over here, which is position 7, and at position 7 we were told on a mismatch to go back to position 3, then what skip is it's this difference here. What is the gap between E4 and E2? And that is 4. And so we can write out this line here, which gives us the amount of skipping we get to do. And when you look at the code that we're going to look at, you might be a little bit confused because you'll see this calculation being done. You'll see this skip calculation. And what all the skip calculation is doing is figuring out the distance back that we should go based on having these numbers already. So if you know to which thing you need to go, and you know its location, how many skips is that? And the reason we need to know that is, remember, we're moving pointers along, and so we need to know how many steps along we need to move the pointer, not just to where it's going. So in the textbook and in descriptions of the KMP algorithm, you'll often see this cpos array called the failure function. And this is another way of saying the cpos array is going to tell us what to do when we fail to match the next letter of our pattern with the next letter of the string. And all of this hard work was being done just to really take advantage of that thing which Thomas and many of you pointed out much earlier, was how can we avoid a lot of this repeated work when we know something about our pattern ahead of time. And now let's actually just look at how KMP is going to run over our string, just to get a visual sense of it. So I would encourage you, I'll try and get you a copy of this little animation because I know the PDF doesn't capture it. And then you can watch it going through. And over here we have our cpos array, which here is called the fail value. And on the side we have the code. And I think I'm going to open up the code on the other laptop because it's going to be too hard to see there. We'll do the code after. Now let's do our analysis of KMP. So in this case, now let's look at the pieces that we need in order to implement KMP, and from there we will do our runtime analysis. So we'll need a few extra pieces of the C programming language in order to implement this, and let's talk about them. So in programming, as many of you are hopefully now familiar with, we call a sequence of characters with a null byte at the end a string. And the reason we have this /0 byte at the end is just to indicate to the system where the string ends. Because we know that inside a computer's memory, ASCII characters are just numbers. So how does it know that the next number along isn't another character? Well, we reserve one of those numbers. Normally on most systems it's a 0, but it doesn't explicitly have to be. But it by convention is. That 0 is going to mark when the character that we're looking at is not really a character, it's just a marker for the end of the string. And so I now have a really bad dad joke for all of you. Why wasn't the string bean afraid of the daddy long legs? Why? Because it had a null byte. And for those of you who are less familiar with Australian insects, daddy longlegs can't bite humans. So ha ha ha. That is the best joke I could come up with. You know what? If you come up with a better string joke, I will give you a t-shirt. Although whoever it was who wanted a t-shirt already hasn't come to collect it. But we will have a bad string joke competition. Sarah, have you got one? So one thing that we're going to talk about a few times in class, and that we already have already, is the notion of syntactic sugar. And this is when underlying in the programming language, something is happening in a more complicated way and can be written in a more complicated way. But the programming language is going to give us tools to hide some of that complexity just by using some language features that allow us to write things more simply. And so in C, a lot of the string functions that you're going to be using, that you've probably seen in Workshop already, are just forms of syntactic sugar. They're ways to write manipulation of individual numbers inside arrays in a much simpler way. Now, we already know that there's a close equivalence between arrays in C and pointers in C, and we're going to see this with strings as well. So you can have a string in C that is represented by a pointer pointing to a sequence of bytes ending in a null byte or a 0. And then you're also going to see an array representation of it, where we know ahead of time how many elements are in the array, and we are just going to go through those array elements until we hit a 0. Now, there are also some very helpful libraries that are part of the C standard library that we're going to use for strings. And this is, of course, because string processing is such a common feature in all programming that it just makes sense to kind of include those as part of the language. And so for us, the ones we're going to use are mostly inside string.h and ctype.h. And these are all the string functions. I would encourage you to actually look up some of these because in your work, you will find some of these useful at various points. Likely for assignment 2, I think, might have some more of these, but also they're just generally helpful functions to have around. And you can often do either spend a lot of time implementing something yourself or use the library function, which has probably been vetted and is more likely to be correct. The ones that and a lot of them also have names that are fairly intuitive. So like is upper, what do we think that one does? Is it uppercase? Is lower? Is it lowercase? There's to upper, what do we think to upper does? Converts it, etc. But you'll notice that these ones take integers. So what do they probably operate on? Do they operate on doubles? Do they operate on strings? Do they operate on integers? They're going to operate on single characters. So you'd have to do to upper in a loop if you wanted to convert the entire string. So let's take a look at a couple of code examples. Okay, our first demo is getWord.c. And this is going to be a file that we will use, that we will include in other programs that we build. So this is going to be our building block to extract a word from input, or extract words in general. So let's look at the comment. Extract a single word out of standard input of not more than limit characters. And the reason we're doing of not more than limit characters for the moment is our tools with arrays, we only know so far in the class how to use a fixed size array. More on how to avoid that limitation will come next week and in future weeks. So let's look at the function prototype at the signature. We have a character array, so an array of characters, and if it's going to be a string, what needs to be at the end of the character array? We need a null byte, and we're going to have an integer limit that will essentially tell us how much room there is in the array to put things in. Because if we go beyond the limits of the array, what will we probably get? This was one of my favorite slides last week. Segfault. Okay, so we have an integer c that was going to be our character that we've just read in, and then we'll have a variable that we use to keep track of the length of the string so far. Now remember, the length of the array and the length of the string so far are different things. The null byte is not going to be necessarily at the very end of the array. It'll be at the end of the characters that form the word. So we might have space for 10 characters, but we might only read in 5. So the right place to put the null byte is at index 5, which is actually the 6th place. And so this is also another place where people get off by 1 errors, because they'll think, oh, I read in 5 letters, so I'll put the null byte at position 4 because arrays start at 0. That's a mistake. If you read in 5 letters, the null byte is in position 5 because the characters are in position 0 to 4. So be careful of that one. So what this is doing is it's first checking if what it's read in is something that is not a character that forms part of a word. So that would be a number, for example, is not part of a word. So fill our variable c, that integer, with a character from standard input. This is different to scanf. This is another way of working. So get a character from the user and store it in C. If it is not the end of file character, so if it's an actual character, check that it is non-alphabetic. If it is non-alphabetic, then do nothing, but just skip over it. Do the loop again. Keep doing this. Keep doing this loop. Read in something, check if it's non-alphabetic. If it's non-alphabetic, keep doing the loop. When it's finally alphabetic, so when we finally see the first letter of a word, end the loop. Okay. Now we also have to check if it is an end of file character. And if it is an end of file character, that means there was never a, the user never entered a word, never entered a character, so just end. Okay, finally, we've actually found a real letter. So the first thing we do is we store inside W that character C. Now, len is going to be how long the word is so far. But there's a bit of a trick here. And I will write this out a little more clearly. Oh, I'll write it out this way to show you what that previous line was doing. The previous line was using the fact that we know that the plus plus is only going to happen after we've filled in the character to give us a trick line that lets us do two things at once. So we'll both fill that character in and also increment length so that next time we do this, we're going to put the letter in. If we just did position 0, next time we'll put it in position 1 or position 2. So that was just a trick way of writing it kind of nicely in one line. My personal preference might honestly be to write it in 2 lines, just because it's a little clearer, and the compiler is going to reduce to the optimal number of instructions anyway. So I don't need to worry there. Okay, now that we've read in one character, let's read in the rest of the characters. So while length is less than limit, and we're doing strictly less here, do the same thing again. So keep checking, keep going through while we've got actual letters, and then store those letters in using the same process as before. Now this step is really important. If you forget this step and then you start using string functions, things will break because your string algorithms are going to keep going along, looking at the next letter, looking at the next letter in the array, looking at the next letter array in the array, and they're only going to stop when they see the null byte. So if you forget the null byte, you'll go outside the array and you'll get a segfault. So when we've finished, when we finally are out of letters to read in, or when we've hit the limit, we need to put in our null byte at the end. Okay, and now we are ready to finally explain the very start syntax that we saw in day 1 encoded in our main function at the beginning here. And we'll take a question from Tom before we do that. It's okay, that one's on.
I'm just curious about, you never specified the size of the array W. So it feels like you're using a dynamically sized array somehow.
So that's just because, let's take a look here. So Tom's question was, you never said how large the array was. So does that mean that there isn't really a limit? The answer here is that this is a function that expects to be given the array from somewhere else in the program, and that place elsewhere in the program is going to specify how large the array is. This won't really work otherwise. So now we are finally ready to explain what looks like a really simple bit of code relative to what we've been doing, but that actually uses these 2 variables that are part of main's function prototype. These are argc and argv that specify arguments to the program. Now we mentioned these earlier on, where argc is the number of arguments and char star argv is a pointer to arrays of characters. And remember that arrays are pointers as well, so this is like a pointer to a pointer. But remember that just like we can think of the array as a pointer, we can also think of the pointer as an array. So we could think of this kind of like, it's not quite identical to, but we could think of it like a 2-dimensional array. And I'm going to be very careful to say it's not actually a 2-dimensional array, but we can think of it that way. The reason why it might be helpful to think about that is because if an array of chars is kind of like a string, then a 2-dimensional version of that is like a whole lot of strings. But again, I'm going to be careful in saying this is not actually a 2D array. It's just a helpful way of thinking about it. What it actually is a series of pointers to strings. So what we can now do is we can run this program, and I think it'll be more intuitive if we see it run and then return to the code. me actually give it a name. Okay, so when I run this program with no arguments, I just run the program itself. What I see is argc equals 1 and argv 0, that first index in the argv array, is a string that contains /progargs. So now let's look at the code. So what the code does is it prints whatever value is argc, and then what it does is it uses this %s format string specifier in printf, which tells printf to print a character, print a character, print a character, print a character until you see a null byte. So it is the string format specifier. And what have we given it as the index? We've given it each subsequent position inside argv. So if argv is an array of pointers to strings, if argv is an array of pointers and each pointer takes us to a set of characters terminated by a null byte, then each time we ask printf to index into argvi, what argvi is a pointer to a string, and so what printf is going to do is to look at that pointer and say, this pointer goes to a whole bunch of characters. I'm going to print those characters one by one until I hit a null byte. So now let's run prog-args with hello there, KJ. And what we're going to see is the operating system will automatically split that up into a bunch of different arguments for us. It'll split it up based on where there are spaces. And now argc is 4, because there are now 4 arguments. arg0 is prog-args, argv1 is hello, argv2 is there, and argv3 is kj. Now, what is up with this argv0 prog-args? Let's see what would happen if I called this soup commander. And I run soup commander, argv0 will now be soup commander. So what argv0 is actually doing is it's giving the program access to know what its own name was, what command it was run with. Oscar has a question again.
Because you recompiled it there, couldn't it just be saving that in memory? Like saving it in the compiled program?
So let's try renaming it and see what happens. Soup commander, call that Oscar commander. Now you can see it's actually doing it dynamically. Now let's try write a very basic string copying function just to whet our appetites a bit, and then we'll move into the KMP implementation. So here are 2 ways of implementing string copy. What we want to do is we want to copy a string from one location into another location. So in this case, I want to copy test1 into the array, into this character array that has room for 1,000 characters. You'll notice one feature here that I'm using, and that's const. Const is a way to let the compiler know that one of the arguments is not allowed to be changed by the function. It's not allowed to, it can read it, but it can't write anything to it. And one of the reasons we do this is because C allows us to write code that uses strings kind of as is, just like the way we might write a number. But because of the way they're set up in the program's memory, if you try treating this as an array that you can write to, you'll get a segfault, because it sets aside that memory specially. And so this const keyword is a way of us telling the compiler that, hey, whenever you get this argument, it's going to be an argument that you are not allowed, that your function is not allowed to write to. It can read to, but it can't write to. So now let's look at string copy 1. This is our nice simple version. So let's write our strings as arrays. We have a source, which is our second argument, and our destination, which is our first. Set up a loop. While the byte that we're looking at is not a null byte, so while we're still looking at a valid character in the string, make the character at destination I the same as the source one, and then just move to the next position. So this is look at the source, look at the destination, copy, 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 until you hit a null byte in the source. We're not looking for a null byte in the destination because the destination is the one that we haven't set up yet. It's the source that we want to look at to find the null byte. Then when you're done, put a null byte in at the end of the destination and you're done. What about number 2? Well, here we're treating strings as pointers, which is perfectly fine. We know this correspondence between arrays and pointers. So the first thing we do, create a new pointer and start it to point to the very start of the destination string. Now what we're going to do is we'll have a pointer source that we read in from the function, and this is going to point to the very start of the source. And now we're going to do the same thing, dereference the source pointer and figure out what's there, and use the dereference operator to store it in whatever P is pointing to, which right now is the start of the destination, and then move them along one by one. And then when you're done, just return the destination. Now, you might ask, where's the null byte gone? Like, shouldn't we put a null byte at the end? Now, you'll notice something kind of tricky and clever being done here, is remember the equal sign is going to return the value of the assignment. So if we assigned like the number 2 to source, then the result of that equals operation is going to be 2. And that's why we've put it in parentheses here. So if source was 2, then we've stored 2 in destination, and then this whole thing would be evaluate to 2. Now what happens if the last thing that we stored was a null byte? Well then that would be 0, and then that would be evaluate to false, and so it would exit the while loop. And so this is a very clever way of dealing with that null byte kind of automatically there. Now let's run our code. I don't think there will be any surprises with this one. Nope. Test 1, test 2, and let's just check what we were printing. We were printing that string str both times. So it has successfully written it in both instances. We are now going to go over the KMP implementation now that we know a little bit more about strings, and we know how to build our failure function, we know how to calculate the skip, and all our pieces are going to come together, and what was a really intimidating and kind of complicated thing to understand should actually become a whole lot simpler. Now again, I'm not expecting that you will, in your head internally, have the whole algorithm. I certainly didn't, even as of like last night. I had to go back and relearn it, and most people I know teach this have to do that every year, but the point is more to be able to do it once, to understand a slightly more complicated algorithm, to work through it and build that skill. So up at the top, I've got some hash defines for the max len, because we know we're going to be using arrays. Got a -1 to show not found. And then KMP in this implementation is going to be in 3 pieces. The main pattern search algorithm, the algorithm that does our processing work ahead of time to build this like complicated finite state automata that we're actually just representing inside an array. And then we just have a function and helper function to print the failure function once we've made it. So what we've got here is just some helper code to actually set up our KMP algorithm so that we can display the results and use it. The only thing I want to show you here is a new type of function that you haven't seen before, which is an F prefixed function. This isn't a formal name. It is a function prefixed by the letter F, is what I was trying to say. And there are functions like fscanf and fprintf. And the reason they're different from the normal ones is they take an extra parameter that allows you to specify where the input is coming from. And this will become important later. But for now, we're just going to say the input is coming from standard in. And standard in is another way of saying the normal command line input that the user is putting in. And standard in is defined inside this file, stdio.h as well. And we've got input for the pattern, input for the target. So it asks the user, what do you want to input? What's the target? and then it will run KMP, which remember the goal is to find a pattern within the larger target, to find the mutation within our DNA sequence. Okay, and here we go. Here is KMP. So let's start with just the search algorithm itself and not how we build the state automata, and then we'll go back and look at the finite state machine. We have two variables, one which tells us at which index in the string do we think the pattern could match at so far, like have we checked if it starts at index 1, have we checked if it starts at index 2, and also where we are inside the pattern. So do we think that we're up to like state E2 in the pattern, do we think we're up to state E4 in the pattern, etc. And then we have variables to represent the total length of the pattern and the total length of the string, just so we don't exceed our bounds. So while there is still room in the target left for us to find the pattern. So remember where I said you couldn't go all the way to the end of the target string, you had to like leave some room so there was enough room for the pattern. That's what we're doing here. Now check if at the location that you're at, the location in the pattern matches the location in the target that you're meant to be looking at. If there is a match, move to the next one. And then if you've reached the end of the pattern, you found the correct index, so report the index at which you started looking for it. So if we said like, we think it might start at location 2 in the target string, this will return location 2. Otherwise, this is where we get a mismatch. Calculate the skip value. And so the skip value, remember, was just this difference between the index and our like CPOS or our failure array. And so this is just saying, move along, skip this many places. So just the exact same thing as we've done before, just in C code. And this line here is, remember how we had to follow the arrows to figure out our new current state? That's what this is doing. It says, look in the failure array for which arrow you should take, and just assign your new state to be the result of that arrow. And then what we additionally have is a small implementation detail. If you look at our picture, if you look at our finite state automata, you'll see I have a special value for the start position, -1, and that is just to make the implementation work out a little easier when you do this calculation for calculating the skip. So that's to ensure that you then get a skip of 0. But the way we are implementing that in our code here is also to have, if you're going to go back before the start, just go back to the start. Okay, and that's it for the core KMP algorithm. And now all we have to do is build this finite state automaton so that we know what the skip value should be. And remember, the way we're building it is looking for suffixes that match prefixes. And so what we're going to have to do is we're going to have to go over the entire pattern and look for these matches. So look at the possible prefixes and look at the suffixes we could generate and check for the ones that match up. So here we have something that looks a little similar, but now we're only operating inside the pattern. So we're going to start at position 2 inside the pattern for our suffix, and we're going to have an iterator as well that's going to go through and look at our different length of prefixes. So why do we start at 2? Well, that's because we already know that if you're at the start, that value should always be -1, just to make that maths work out. And if you're at the first location, that should always be a 0. There's not like, for our LMLS string, there's not another E to go back to earlier. So if you mismatch, you're still like looking at that to see if that letter E is matching. Okay, while we're still inside the pattern string, so this is going to be a loop over the whole pattern string, check if where we're looking at from our suffix is matching a part of the prefix. And so if you look over here, we're starting C at 0. So that's going to be where we look for the prefixes on that version of our pattern string. And the other side of the pattern string is going to look where we're actually looking towards the end of it. So increase C. And then what we're going to do is at this point, if we do have a match, that means that we should be able to skip at least that one step. And so update the failure array to say we should be able to skip at least that one step, and then move the suffix pointer along as well. If you didn't match, and C is bigger than 0, so this means if you've already made your way through part of the prefix. So C is 0 when we haven't matched any of the prefix. And so this is saying, okay, if you've already managed to do some matching of a prefix thus far, store how much of the prefix you managed to match. Otherwise, we haven't matched any of the prefix, so it should just be 0. There's no earlier place that we could go back to. And so what this is essentially doing is it's doing the check to see, okay, are there bits inside the pattern itself that match earlier bits of the pattern itself? And so where there are those places, we can go back to that earlier position. We can draw that arrow. Otherwise, we should just record the longest one that we'd gotten up to that thus far. And that's really it for all of KMP. That's the whole implementation of KMP. It is a little complicated conceptually, but once you get the core idea down, even if you can't explain every single line of code very fluently, you can at least figure out how the thing is working overall. I will say what typically gets tested is, do you understand how to build that, that finite state automaton and write out the table of the failure function? Because that really shows, have you gotten the core idea? We won't test you, can you implement this code, because it's kind of finicky, but you should at least be able to draw out that, okay, how much should I skip as a result? Now the trick there is to remember, I think it was Oscar's question, which is why can't you reuse all the work? KMP only reuses very particular types of work, and that's where you have this duplication between that prefix and that suffix. Now let's do our worst case analysis. So there are two parts to KMP that we just saw. We've got this pre-processing step where we build our finite state automaton, and then we have the search that we might run as many times as we need. But remember, this search is going to be with a pre-specified pattern, because the reason why we're able to do a faster search is because we've pre-processed the pattern ahead of time. So let's first analyze the search work that we have to do. And so our search is going to work as follows. There are a maximum of n minus l plus 1 possible starting positions. We've gone over this lots of times because there isn't enough room for a 10-letter pattern when you're at the second last letter of the string. At each position, we do one comparison for the first position. So we have to at least look at the current letter we're up to. And at each position, we're also going to do a comparison for the position that C reaches. So remember, C is going to be our iterator here for within the pattern. So what we can do here is we can count how many backtracks we've had to do, and so that'll tell us how many extra comparisons we've had to do as a result of that backtracking. So remember, at every point, like when we were at, I think it was E4, we were able to backtrack twice, and each time we did a backtrack, we had to look at the next letter to see, okay, should we have been at E4, should we have been at E2, should we have been at E1, and each of those is an extra possible comparison. So we have to count those backtracks up, and for each backtrack, there's another possible one comparison. So our big question here is, how many backtracks are there altogether? So for each time we backtrack C, we're actually moving S, our guessed position, along by the same amount. Let's say I guessed that the longest prefix was 5 characters along, and that required a backtrack of 2. If that fails, then I'm going to slide my pattern string along at least another 2 spaces. So that means when we backtrack, we're not actually giving ourselves more work overall substantially, because we're moving along our guess at the same time as we're moving our backtrack back. So we compare each time we move backwards with each time we move forwards, and this can only happen a maximum of n minus l times, where l is the length of the pattern. And this is less than n, so n is much bigger than L, let's just ignore that L there. So this is going to happen O of n times. And then worst case, if we match finally at the final location, that's going to be an extra L steps that we do, because we need to then go, if we keep backtracking, and then finally on the last one, we match position 1 in the pattern, position 2 in the pattern, position 3 all the way up to L, then that's going to give us an extra count of L. So let's add it up. We get n possible moves forward, plus the n extra steps that we've done as a result of the backtracks, plus L for if we happen to be unlucky on that final one and match only at the very end. What's the big O of that altogether? Is n or L bigger? N is bigger. Do we care about the 2? No. Okay, that's an O of n worst case search. But we have to figure out also how much work we had to do in the pre-processing stage, building our state transition table for our finite state automaton. So if we look back at what we did, we were doing this loop, just going through it once, and we want to count how many comparisons we do. So let's look at our code, and we have 3 conditions. We have the condition where we move C forward and S forward. So our loop is going to iterate until from S goes until M. So this is a step forward, and this can only happen up to M times. And in this case, we're also moving S forward. All we have is this branch where we're not moving S forward. And so what we need to do is we need to figure out, okay, if we take C backwards, how many extra comparisons is that going to give us? So we only do an extra comparison in this case. Number 1, if we've mismatched, and also if there's an arrow for us to follow backwards. If we've mismatched and we're at the start, then we don't have a place to go backwards to. But if we do this, if we're doing this jump backwards, that implies that we'd already made some prior progress, because you can't go backwards if there's nothing to go backwards to, and so there must have been some progress. Therefore, for each time that we both mismatch and backtrack, there must also have been a match. So we could do a maximum of 2L comparisons. If you add up, okay, for every time we've gone back, we must also have gone forwards at least once, and we'll also know that we're going forwards a maximum of L times. So add those up, you get 2L. So for our overall KMP algorithm, we get 2n plus L plus the 2L from the pre-processing step. We get big O of n for n is bigger than L. And n has to be bigger than L because our pattern has to be, our target has to be larger than our pattern. So why is KMP decent for DNA? Essentially because DNA, as we talked about before, has fewer letters, so it's going to have a lot of repeats. So this makes something like KMP actually a pretty good choice. Now I will say that in practice, because we're in a first year class, KMP is not the algorithm that really gets used, but over the next 25 minutes, we'll go through some of the stuff that is a lot closer to actually being the real thing that gets used to find mutations in a large string of DNA. So this is our final act for today, which is linear time isn't always good enough. So think about the actual things we do with pattern searching in an ordinary day. What we've done thus far in the class, we've been able to make one search over one pattern, worst case linear time. But what if we're not doing one search over the target string? Let's say we've actually done this DNA thing. We might be looking for a whole bunch of different patterns within that DNA. Or we might be doing something the opposite. We might be using one target string across multiple different patterns. And depending on the real world scenario that you have in front of you, you might be willing to do different types of pre-processing and store different things ahead of time in order to make the operations that you're going to be doing a lot more efficient for your use case. So let's take a slightly different example that we'll bring back to our DNA one a little before. Should we use KMP to build a search engine for text over the books in the Bailey library? Now, Oscar, can I have that microphone? Oh. You're going to help me out. What was your name?
Mike.
Michael. So Michael's going to help me out with this problem. Okay, how many books are there in the BLU library? 30 million. How many letters do you think there are in the BLU library?
10 trillion.
Okay, so let's put some more concrete numbers to this. So the library contains approximately 78 kilometers of shelved material on 101 kilometers of shelving at a shelf utilization rate of 77. Do you have a calculator on you?
Yeah, that's the 5 nonsense.
Okay, get ready. So how thick is a book?
On average,
Yeah, how thick's a book?
say 6 centimeters.
Ah, that's a pretty hefty book. We are talking about the BLU. Let's just go with 10 millimeters. Yeah, I don't know. So that's approximately 100 pages, I would say, is about 10 millimeters. Now we know the BLU books are thicker, but this, knowing that 100 pages is about 10 millimeters will give us a way to go from here. Okay, how many words on a page? 300, that's exactly what I had down. Length of an average word-ish? Yeah, well, let's go with 5. 5 seems good. So how many characters on a page? Yep, 1,500 characters for every 300 words. So how many characters in 10 millimeters?
Well, it'd be 100 times that, right?
Which is, so you had one.
Is it what?
That's 150,000 characters per.
Okay.
Yep. Oscar, you have your hand up. Yeah, but like we're doing order of magnitude here. Right, so let's double it. So we had 150,000, 300,000 per 10 millimeters. We have 78 kilometers of shelving on 78 kilometers of shelved material. So how many times does 10 millimeters go into 78 kilometers? Everyone should be trying to do this one way or another. Yeah, 78 kilometers and 300,000 characters per 10 millimeters.
Do we need like an area for the books?
Not really. We've done the pages. We need order of magnitude here.
Okay, so there's about, I've got,
Give me in exponential form, like 10 to the what? Characters in the BLU?
yeah.
No, where that's multiple orders of magnitude off. Anyone got it? My estimate is there are approximately 10 to the 12 characters in the BLU library based on these numbers, which is 1 trillion characters in the BLU. So let's say that we can do 10 to the 10 operations per second. How many seconds to search for a pattern in the text of the BLU library? Somewhere between 10 and 100 seconds, depending on exactly how we do our constants. So this is 10 seconds for every time we want to search for a book for text in the BLU library. And this is on an entire core of a processor, of like a modern processor inside the BLU. So should we use KMP alone to search through the BLU library? No. And this is actually what the task that we've just done now is actually something that you should do if you were building an algorithm, both theoretically but also practically. Going through and figuring out, okay, what's my actual use case? Can I put some numbers to it? They don't have to be entirely accurate, but can I get order of magnitude? And if order of magnitude is close but not there, can I make my estimations a little more accurate? But this is clearly not going to work because let's say 10 of us are searching Now we need 10 computer cores, each to be working for between 10 to 100 seconds, so we can do 10 searches of the value. Not a good idea. So O of n is not good enough for this case, which you're like, whoa, I thought O of n was pretty good. But if you're searching the same corpus many times and this corpus is large, linear search is not going to be fast enough. Now, you might complain at me and you'll say, but O of n is worst case. That's true. And so you might actually get much better practical performance, but still, this is not the way that we should be thinking about the problem. Let's see if we can find our way to do much better. This is just like our DNA example with many, many, many characters. We don't want to do just one search for one pattern. So our idea here is that we're going to be able to do a trade-off. So you've seen this before. This is all about our space-time trade-off. This is, can we use some kind of data structure, some kind of memory to make repeated searches efficient? Now, I put it back together. I spent a really long time. I had to collect all the pages. Yellow Pages loves me. I'm their biggest remaining customer. But I will get someone to come down. Who's got a microphone? What was your name? Thomas, was it? Michael. Do you want to pass the guy behind you? Sorry, you were Tom, you were Michael. Yeah, come down to the front. Yeah. Who's ready to have this thrown at their face? Yeah. No throwing today. OH&S gave me a talking to, and so now we're okay. So let's say I'm looking for medical practitioners.
Medical practitioner.
Yeah, so turn your microphone on. It's on, great. Remember to hold it up nice and high. So if we're looking for medical practitioners, practically what do you do? If you were to use one of these?
Oh.
This is the problem. No one's used the Yellow Pages anymore.
Yeah, never seen before.
Okay, so what do you normally do with like a really fat book if you need to figure out where you want to go in it?
First go through the contents.
Contents, or what's another word for contents that's often used for like really large reference books? Anyone know? An index, yeah. And so it's kind of like a table of contents, and let's look at the beginning. No, that's a calendar. There we are. See, it says, can you read that out for everyone?
Fast find index.
Yeah, I'll show you. It says in really big letters, fast find index. So if it works for humans, maybe it works for computers as well. So tell me how this index works.
So if you found medical, then you go for M.
So it's listed we've got like an alphabetical ordering here.
Yes.
And then if we're looking for medical practitioners, which is a big list somewhere else, we can go to the index and under the letter M.
And go for medical and...
See, medical... Let's go for medical research. That'll be good enough for us.
Page 88.
Page 88. And now if this is an array, we can jump right to page 88 without needing to do really very much search. How much did we have to search through?
What do you mean?
In order to get to page 88, how much searching did we have to do?
Two steps.
Yeah, we looked at the index and it took us a little work to go through the index because we had to find the letter M, but the index, was it sorted or unsorted?
Sorted.
It was sorted, so what technique can we use to quickly find where we need to go in the index? Do you remember a search technique that we had?
Yeah, it's like, I forgot its name, but it's like divided in half.
Yeah. So what in computers, the two things that come in twos are binary, right?
Binary, yes.
So what's the search called?
Binary search?
Binary search, yeah. So we could use binary search to do our really quick searching through the index, and then once you found the place in the index, how many steps did it take to get to the right page? In theory?
Only one.
Only one step.
Yeah.
We're almost there. Humans are not as good at indexing into arrays as machines, but there we are. You want to show everyone?
Medical research.
There we are, medical research. Can we have a round of applause? I'm not going to throw the book at you today. I'm sorry if that's what you were excited for.
No.
Remind me your name again?
Hugo.
Hugo. So Hugo helped us out with using an index. And that's it for the yellow pages for this year. So this gives us at least an intuition for a much more efficient way to do searching when we're going to be doing searching over the same corpus over and over and over. We're going to use an index. This is storing data by a keyword or some other shortened listing. So in this case, even if we wanted to find a particular medical research outfit, we wouldn't go by searching for the name of that particular medical company. Instead, we go to the index, and that gives us exactly the page we need to go to, and then we might need to do a little more work at that point, but not very much. We're definitely not searching through the whole corpus. And so for the yellow pages, this act is quickly find a category in a list of categories in the index, and that takes us to a final place where individual items of that category is stored. A book index is quickly find a word in a list of words that might appear elsewhere in the book. And the question is, can we make this work for arbitrary patterns, or does this only work for like yellow page businesses? I don't know. So this takes us back to lecture 0 of the, to lecture 1 of the semester, back to find repeats. And we're going to bring back finally our very first data structure that we had in the class. And this was our suffix array. And we're going to use this for the remainder of our time. So if, for those of you who don't remember, the way we create the suffix array is by writing out at position 0, we have the whole string. At position 1, we have the whole string except for the very first letter. Position 2, the whole string except for the second letter, and so on and so forth. And then we can, so I've written that out. And now what I've done is sorted in lexicographic order, so alphabetical order, but also accounting for the symbols. And what I've done is I've also kept track of the indices. So when I've moved one of the strings, I've also moved its corresponding index, which tells us where that suffix started along with it. And then what I can also do is I can create a new array which stores those changed starting locations. So just to go back, write the suffixes down with the indexes where those suffixes start, sort them, and then put those sorted numbers into an index of their own, into an array of their own. So now, is ls in our target string? So let's say our target string is this seashells, and I want to know if ls is in there. So I'm going to have another friend help me out. Or maybe you can do it from there if you want. That's easier. Yeah, you can do it from there. Okay, so I'm looking for the string ls in my target string. My target string is she #sells #shells. And I'm looking for ls. And you can just, as a human, you can tell me, is ls there somewhere?
I can't see.
Oh. In the word she sells shells, are the letters ls there anywhere? Yeah, they're there. Hold the microphone up so people can hear you. They're there?
Is 7A?
Yeah, they're in location 7 and 8. And that's good for a human, but remember, computers can't look at the whole thing at once. So they're going to have to use something like the data structure that we've just built. So can you see anything interesting about the data structure we've built that could allow us to search really efficiently? It's this thing over here. Is there something about this that'll make it really easy for us to find patterns? So is it sorted or unsorted? It's sorted. In what order? Is it order longest to shortest?
Longest?
No, it's alphabetical order, right? So E is at the top and S is at the bottom. And so when we have a sorted list, what's a really quick way for us to search through it? We talked about the algorithm right before. Hugo mentioned it. Might be easier if you don't look there and forget about that. When we have a sorted array, what's the fastest way of us finding something in the sorted array? Yeah, which search algorithm? Hugo said it before. We throw away half the problem each time, right? What was that? Do you remember what it was called?
I can think about the way, but I
It was binary search, right?
Oh, yeah.
Not complicated. So we can just do binary search here. So you're going to help me out. So let's look at our thing, at our array. And binary search works by pick the point in the middle. So what's the middle of this array? Of this one?
Yeah.
It's like somewhere about there, right? And is L before or after H? After. It's after. Okay, so let's throw away, the top half. Is LS before or after S? Before. So we throw away the bottom. Now let's look over here. What's at the middle point?
LS.
LS. Ah, so we found it. There is an LS starting at location 14. There is an LS at 14, so our binary search has worked. If we go, that's 9, 10, 11, 12, 13, 14, you can see an LS there. And so by building this index ahead of time, by building this suffix array, we've been able to accelerate our ability to find any of the suffix patterns really quickly. But on the other hand, we also had to store a whole bunch of stuff in the computer's memory, so it wasn't quite free. We also had to build it. So now we can ask, how efficient is suffix array pattern searching? Well, we only have to build this whole thing once, and then we're going to search over it many times. So what KMP was doing was speeding up one search by remembering the pattern. Suffix arrays are going to speed up many searches by pre-processing the whole text, or in our case, pre-processing our whole genome. And this is actually the basic technique that is really used today for searching through genomes. So let's look at the search half of this. The search half is just binary search, but it's different from normal binary search over numbers because what are we comparing? Not numbers, we're comparing strings. Strings are numbers, but they're sets of numbers and you have to compare them one at a time. And so there are n possible matches, and L is the length of the pattern. So accounting for the fact that we might have to search, at each location we might have to check up to L letters, we're going to get L log n instead of just our plain log n for when we were just searching through numbers. So that is the search part, very easy once we've built the suffix array. Turns out that suffix array construction is actually a really hard and really interesting problem from the perspective of figuring out the best algorithms. So I'll go through a couple of very quick remarks on suffix array construction, but the details of suffix array construction using the more sophisticated things beyond the class. So the basic ones, which are in scope, so to build a suffix array, add n strings, each of which are of maximum length n, into an array. So this means just go through the string, take all the letters, take all but one of the letters, take all but two of the letters, take all but three of the letters, copy them in one at a time, and then sort them once you've done that. That's going to take n steps to go through the letters, and then n log n times n to do the sort. It's times n because this isn't a sort over integers anymore, it's a sort over strings. So that gives us an extra multiplicative factor there. So this gives us n squared log n character comparisons. Not great. I mean, probably can do it once if you really need to over a small corpus. So we can improve this by using a slightly cleverer way to compare and sort suffixes, and then we can get n log squared n character comparisons. So that's a meaningful improvement. That's actually quite meaningful. But we could do a better job of sorting our suffix. So rather than this complicated, rather than this simple but brute force method of doing the sorting, we can use a slightly better method of sorting. And in this case, we're going to use an algorithm very similar to quicksort. So similar, in fact, it's still called quicksort, but it's ternary quicksort. Instead of splitting into 2, we're going to split into 3, and we're going to do this based on the length of the strings. And so what we're going to do is we're going to partition our elements into things that are lexicographically after, things that are lexicographically before, and things that are lexicographically the same up until the depth that we've looked at. So this is like saying, look at all the strings, but only the first letter. Group the ones that have a first letter later, obviously. Group the ones that have a first letter that's before, and then group the things together that where the first letter is the same, but they're not sorted yet. So it's not like in normal quicksort where you know your middle part of partition is totally sorted. Here we only know they have the first same letter. And so this strategy does allow us to get a better complexity here. So this is roughly how it works. Split it into 3 pieces. Everything that is lexicographically obviously before, everything that is after, just based on the first letter, and then everything that has the same first letter, but is still not in a total sorted ordering. And then we just do this over and over and over, just like we would do with regular quicksort. So that is a better method. And so this is the start of an algorithm known as radix sort, which is, again, I'm not going to go into the details of how to distinguish radix sort from ternary quicksort, but essentially you can divide up into as many different partitions as you like, depending on what makes sense for your data. So for strings like this, it makes sense to divide into 3 partitions and then use one of the partitions as increasing depth for the letter. But you can get a little more sophisticated based on what you know about the language and based on how many characters there are. So for example, in Chinese that has far more characters, you might use a different partitioning strategy. Instead of partitioning into 3, you might design your sort a little differently. And so why is this of benefit? Well, it's the same kind of idea as KMP. We want to avoid repeated work. We want to avoid comparing things that we've already compared. So for everything in that middle group, we know they already have the same first letter. So when we continue our sort, we should not compare any of those items against each other on their first letter again, because that would be wasting work. And why does that work? Well, it's because we're dealing with a limited alphabet size. This works particularly well because we have a limited alphabet size. We have only 26 letters, and so the chance that we have this like nice middle group where we can save some repeated work is actually reasonably high, particularly given the distribution of English words. So we know that some letters are going to be far more frequent, so we're likely to get suffixes that start the same way as well. Can we do even better? Well, there are very, very fancy suffix-array construction algorithms that can be done in big O of n character comparisons. And these are so fancy that I personally don't know how they work. This is at the level of research. And also it's some of the research that's actually been done at this very university. So here is a nice citation to one of some recent recent-ish 2016 work on linear time construction of suffix arrays, and this was by Andrew Turpin, who was a long-time staff member here and who only left a couple years ago. But more than that, you might recognize that name, who is Professor Moffat, who teaches the other semester of this class, and he has also worked on this very problem. So you see, you're only, 6 weeks in, and for some of you, this is your first ever class in computer science at uni. You're already touching the very edge of what we know about computer science. So there have also been some recent advances that allow us to reduce the amount of space that things necessarily take to do the construction, or that allow us to take advantage of alphabets that have fewer or more characters. And in fact, I've got this beautiful table of all this recent research which says, well, under this condition, you can get this set of trade-offs for space, this set of trade-offs for time. And the idea of showing you this is just to show you, this really is stuff that is still happening today. And if you love suffix arrays like I do, you can go and do research in our school on finding ways to build them better. So how efficient is suffix array pattern searching? Well, we can do suffix array construction in O of n and search many times in L times log n, where L is the length of the pattern. And our lesson here is, if you're going to use an algorithm many times, trade repeated work for upfront work. So what's our overall message from the lecture? We can sort in linear time when we have some structure. Real world data does have this structure. Long strings are rarely totally random. So what we can do is we combine the natural structure that we find in the real world with specialized algorithms for efficiency. String search is going to get faster when we stop throwing away the structure. Find structure in the pattern, find structure in the corpus, and your life will be better, happier, and faster. Thank you very much, and I will see you all soon.